Mhm. Oh, that's actually charged. Okay, good. Let that be. All right, share my screen. Start the broadcast. Give me just a little bit, a few more minutes to kind of finish getting set up here. Let's go to the over there. Here. Let's see. That's correct. Stay as a participant. And let me check something. I think if I go. Okay, I don't see them at the moment. Okay, so I'm gonna work back right now. I'll try again towards the end of class. Let's see if I can remember. All right. Sorry about that, guys. I'm trying to wake up. I don't know. It's strange. Like I just got finished doing a match, right? We won, right? I lost a lot today, but I was like, it's okay. It's not a big deal. But I had all this energy. Then I go to start class, and I'm like, okay, time for a nap. I'm like, no, it's time to wake up. All right. So let me see. So we're pretty much in the home stretch, right? Today is essentially the last of the new material that you're responsible for. I might do a bonus lecture or two that you're not necessarily responsible for. Maybe not. I hadn't decided just yet. But today is the last of the new material that you are responsible for. Section 4.6, integration techniques, integration by parts. I think last time we did integration techniques by substitution. So we worked several examples exploring that, and so we'll do the last of the pertinent information today. I want to say that course evaluations are available, so feel free to do that at your leisure. You should have gotten an email about it. I'm pretty sure there's another way you can access it, but I think you maybe access it from Bannerware or something. But it should be in your email, and you can do that there. Let's see. I can't think of anything else. I don't see the student here. Let me check one more time. Yeah, I don't see him, so I'm not gonna worry about it. Let me see. And then there was a student that asked about like assistance with one of the questions. So I sent a reply. So hopefully it worked for you. Just let me know if you still weren't able to get it. That we can go further into depth on it. I can't think of anything else. So let's just kind of hop into it and get the party started. So we're continuing chapter 4 in integration with section 4.6, integration techniques, integration by parts. Let's go like this. Oh, and that is the student. Okay. So yeah, let me say this at least. Every day. Jump in my new EV with me. Okay, so every year, about this time of year, Morehouse holds their annual Math Awards Day ceremony. And so congratulations to our recipient for this course, which is Mr. have Kendall Winston, right? So I sent an email about last week or so. So feel free to come out tomorrow. So just check your email for that. I think there will be food, right? So something to consider and something you can definitely put on your resume. And so for this course, no, we haven't officially finished. It's just at the time when I went to go compile that list, that was the student with the highest average, right? On just across the board. So and it's not, he wasn't up there by himself, by the way. Like it was several students that were like, all of you guys were like neck and neck, and I was like, okay. In the past I used to do like the top 2 or 3, but then I would have like 20 students up there. It was crazy. So I was like, okay. So this time I said, okay, I'm just doing the top for each course. So congratulations to Mr. Winston. Hopefully we'll see you there tomorrow. So just let me know if you intend on showing up or not, so that we can be sure to save a spot for you. You can bring guests as well.
I'll be there tomorrow.
Okay. Then if anybody wants to see me live and in person, I will be there. I was like, I just needed somebody to like RSVP, and I'll show up.
So, and you said you'll send an email tonight, right?
I can. I'll just forward it again. I sent it like about last week sometime, either Tuesday or Thursday. So if you just kind of go back in your emails, you see something from me about Math Awards Day. Do a search for Math Awards Day, and you should see it. The information. It's tomorrow, Tuesday at 4 p.m. in the Dansby Hall Auditorium. All right, so Math Awards Day.
Okay, you said 4 p.m.
Yeah.
Okay.
Yeah, just check your email just to confirm that information. And again, you guys are welcome to show up. It's food. There will be food at some point. And it's just something. So just something that, just a nice little celebration or whatever. Yeah. Okay. Yeah. So anyway, okay. So I just got to reset. Okay. So yeah, let's go ahead and get into this last part here. So we're rapidly approaching exam 2, right? And so exam 2 was going to cover chapters 3 and 4, basically the second half of the information for the semester. So once we finish this, we'll do a little bit of review. I want to say exam 2 should become available on Sunday. We'll check that a little bit later. So it should become available on Sunday for the first 7 days, unlimited attempts. You can earn up to 100%. You know those details. So.
Professor, that's our final test, or no?
That's exam 2. And then after exam 2, we're preparing for the final exam. Final exam is cumulative from like the beginning to the end. And that'll be during the week of finals, the final exam. Yeah, that's a good question. Okay. I can't think of anything else. Yeah. Okay. So a few objectives here. 1, evaluate integrals using a formula for integration by parts. And then 2, solve applied problems involving integration by parts. Some of the main takeaways here are like, we kind of introduced this thing of what is it called? Like, for whatever reason, that name escapes my mind right now. The differential, right? So we started by, the whole time we've been talking about how to find a derivative, techniques and application, this, that, and the other. So when you go to find a differential, you find a derivative like normal. And we kind of explored 2 different ways of finding the differential. I think the way the book does it is like whenever you take the derivative of y, you put dy by dx. Everything else you take the derivative like normal, and then at the end you use algebra to isolate your dy and move your dx to the other side, right? So it's called a differential. And so that comes into play like when we were doing our substitution technique. We had to have the differential, the whole form, to show up on the right-hand side before we can use the substitution technique. So the integration by parts, this is like an extension of the substitution technique. So let's see it in action. So the integration by parts formula, the integral of u dv equals uv minus the integral of vd, right? Jargon, let's just see it in action. My pen is ready to go. I'll read through this. So tips on using integration by parts, 1 of 2. If you have no success using substitution, try integration by parts. So you might try substitution first. If that doesn't work, then you're going to try this technique. Use integration by parts when in integrals of the form, the integral of f of x, g of x, dx, okay? And then match it with an integral of the form, integral of u dv. We're going to see, I'm going to go into the details of how to do this momentarily. By choosing a function u equals f of x, where f of x can be differentiated, and the remaining factor dv equals g of x dx, where g of x can be integrated, right? So, we're going to use integration by parts when we have this form integral of f of x, g of x dx, where again, the main takeaway is that f of x can be differentiated and g of x dx can be integrated. So that's the trick. You're trying to find one form that you can differentiate and the other form that you can integrate. Then once you get that form proper, or the proper form, then we can apply integration by parts. More tips. So find du by differentiating. Wait a minute. Find du by differentiating and v by integrating. And then if the resulting integral is more complicated than the original, make some other choice for u and dv. And then to check your solution, differentiate, right? Okay, so let's see it in action. This guy. Okay, so let's see. We'll do. So we're trying to find a proper u. What's the integral of that guy? Okay. So we're looking for a u and a dv. I guess we can put the. Let's see. If that's our u, we can say. Let's go our du, and then we say our v and our dv. Okay. So let me see if we take that derivative. Okay. So we're looking for our u dv. So we're just going to kind of get a check. Let's start off by, let's try natural log of x is our u. And so that will make our dv dx. All right. We're just trying something. We're going to see if it works. So if natural log of x is our u, then our du will be what? 1 over x or dx over x. Okay. If our dv is dx, then the integral of that is what? Just x. All right. Is that okay? So now we have our u dv. Okay. So the way the formula kind of goes, we're going to say what the integral of u dv equals uv. So uv minus the integral of v du. V du, all right? So the trick is to try to find the proper u along with the proper. Let's do this color. Again, we're trying to find the proper u along with the proper dv initially, and then you kind of fill in the blanks, and then you apply the formula. Right? Let's keep going. Okay. So we got our u dv. All right. I think we're good there. So now let's see our u times our v. So that would be what? X times the natural log of x minus the integral v, which is x, and du is dx over x, all right? So x, I'll write it out for now. So it's going to be what? X over x dx, all right? So those guys are going to cancel. So it's really just the integral of dx, all right? So then the integral of dx is what? X. I think we're pretty much there. So it looks like this result is going to be x times the natural log of x minus x plus some constant. And so we're fortunate we were able to get to the end. We can check this by taking a derivative. Yeah, so let's do a quick check by taking a derivative. What color I'm going to use? I'll use this color. I'll just say it's the check. We're just going to check. So if we take the derivative, we have to use the product rule, which would be what? The derivative of natural log is dx over x. We can write it as dx over x. So the first times the derivative of the second plus the second times the derivative of the first, which is just going to be this. Okay. The derivative of negative x is going to be what? Negative 1? Or minus 1 dx. And the derivative of a constant is 0. These guys cancel, and then these are gonna and I think I'm missing a dx here. Right? And I think we get the desired. That's what we wanted. All right. So when we took the derivative of the result that we got back to our original. Because that's a 1 dx minus 1 dx. They essentially cancel. And then again, like I said, I forgot to write that additional dx when I did that second part. And so it all came together. Okay. Okay, so that was us. Let's compare it to the way the book did it, and let's try to get some more examples in. So let u be the natural log of x. I think that's what we chose. So then again, that's the hardest part, is finding the proper u and dv. So you choose a proposed u and a proposed dv, and then once you have your u, go ahead and find your du. Once you have your dv, you got to work backwards to find your v, right? And so we did all these parts. Okay. And essentially, yeah, we got that same result. Let's work another one, right? Because I feel like that one, again, like we might do like we did last time if we have time. If we finish kind of early, which we might, looking at the slides, we'll come back and work these quick checks. But for now, I'd like to go into the next example. Okay. So we're gonna give this one a go, right? I'm at first glance, I'm tempted to do the same thing I did last time. Right? So something along the lines of like, let your u be the natural log of x. Let's see if we can clean that up a bit. And then so we need to find our du. And then we're gonna find our v, and we're gonna choose our dv. It needs to be what? X dx. Since we've already used the ln, we still need to have the x dx. So our potential dv could be x dx. Let me think about this. X squared v du. Okay, let's keep going. Let's just keep going and see what happens. Okay. So if our u is the natural log of x, the derivative of natural log is du over u, or in other words, dx over x. So the integral of x is what? X squared over 2. So this guy is going to be x squared over 2. Okay. So now if the original is our u dv, then the formula, I'll write it again. I mean, I don't really feel like I need to, but I will. So the integral of u dv equals uv minus the integral of v du. Okay, so we're just, the first part was kind of given, so we're going to kind of start with the uv part. So u times v, okay? So it looks like we have x squared over 2 times the natural log of x, that's the u times the v, minus the integral of v. Now we got this x squared over 2 du. So then that's, so times dx over x. Okay. We get some cancellation or simplification going on. This guy cancels one of these guys. You know, we could move that half to the front. Essentially, we're just taking the integral of x, right? Essentially. Or 1/2 x, however you want to look at it. All right, so if we keep going, it looks like we have x squared over 2 times the natural log of x minus, it looks like it's 1/2 times x squared over 2. So then it's going to be x squared over 4 plus some constant. Okay, if anything isn't clear, feel free to unmute yourself to get my attention or type in the chat and we can talk about it. I feel good about this. We could check by taking the derivative. I'm being lazy. I just don't feel like checking. I'm just going to kind of use my prepared notes, but I feel good about this. Yeah, let's check. I mean, I'm going to use my notes. Okay, let's examine several choices for u and dv. So now, first they tried, okay, let's let u be 1 and dv be all of this. But this won't work because we don't know how to integrate that confusion, right? At the end. So they're gonna like, okay, let's choose some other grouping. Okay. So then they were like, well, let u yeah, okay. They said let the u be x natural log of x and dv be dx, but then I think it just makes it more complicated. Like when they, let me see, if that's our u, then you got to take the derivative and our dv, and then once they get those different parts and they try to apply integration by parts, it makes an integral that's more complicated, right? So if you find that happen, you might be like, well, let me try doing a different grouping, or let me either try a substitution or let me try a different grouping. So here they realized that they made the integral more complicated, so they were like, okay, let me just try a different grouping because the original integral is there with something else, right? So it's not reducing, it's getting more complicated. So let's try a different grouping, right? So then now I think they finally get to the grouping that we chose, was let u be the natural log of x and dv be x dx. So then from there, from there it's history, the same thing that we got, right? Okay. So these are fun. This just takes practice, exposure, asking questions, digging, patience, grit is just what it takes, But I would be doing you a disservice if we never, this is like the culmination of the whole semester. Like if you get into a calculus course and you don't at least get to this topic of integration by parts, then a disservice is being done to you. So, with this concept, this is like pretty much everything, right? Because again, the first 3 chapters was all about the derivative, and then it's chapter 4 is on anti-differentiating, right? The reverse of derivative, right? And so these are like major techniques that you should at least, not if you master it, but at least be exposed to in the calculus course, all right? Okay, let's keep going. Okay, so we want to try integration by parts with this guy. That I feel like would make it worse. Okay. Okay, so I'm gonna try something, right? I don't really know, like I don't really look at these ahead of time. So I'm just kind of doing this off the cuff. Okay, so let's try our u. At first glance, I was like, okay, I'm tempted to say let's let it be 5x plus 1. All right, so then we need to find our du. And then we're going to have our v, and we can choose for our dv. I'm thinking x dx. Okay. So let's just kind of go with this train of thought and see what happens. So if that's our u, then our du will be what, 5 dx. If our dv is x dx, the integral of that guy is what, x squared over 2. Okay. So now the original, I might need to change it. We got the square root of u. Give me a moment. We got the square root of u dv. Can we break those apart? Okay. I was avoiding it, but I might need to choose something different. Because it's not matching all the way. We're not getting we're getting like let me think. Wait a minute. Wait. Let me think. So like in the form that we're getting right now, we're getting the integral of square root of u dv. All right, but we need we need u dv. And I know I could choose another one. I was kind of avoiding that radical, trying to like simplify it. Let me think about this. uv. Okay. All right, so I'm gonna back up. Because the square root is throwing me off. So what I'm gonna do is go for the thing that I've been avoiding. And so the change that I'm going to make, I'm going to try letting my u, I'm going to try letting my u be this guy, the square root, right? So then when we go to take the square root, I think it might get a little bit nasty, but we need to just see what happens with it. So when we go to take the derivative, right, we're going to have what? 1/2 5x plus 1 to the minus 1/2 times 5, right? There's a 5 out there we got to account for. So it goes there, okay? Dx. Okay, hopefully VDU, see, I don't think that's helping us. What else? I think there's some trick that I'm missing. Because x dx is fine. What am I missing? Because if we do our VDU, that's going to make it worse, right? Substitution. Okay. If we let our u be that, can we do substitution here? Let me see if I can do substitution. I'm trying to get it without looking at the notes. And I feel like, that little alteration was making things worse. So I was like, okay, let me try something else. So let's try a substitution here. For instance, if we let our u be what? 5x plus 1, our du will be what? 5 dx. How can we get an extra x in there? We get our dx. Oh, okay. I think I got it. I got it. If our u equals 5x plus 1, right? So from there, we can do subtract 1 and divide. I don't know if this is going to help us. But we can isolate the x, right? We're going to get u minus 1 over 5. So now we have x in terms of u. I think we can do the substitution. Let's apply this substitution, right? Let's just apply this and see what happens. I think this was the trick here. Okay, 5x plus 1 is our u, so that's going to become what? The square root of u. X is what? U minus 1 over 5, so we're going to include that. Okay, we're almost there. So we got this u minus 1 over 5, like this. We got our integral, and our dx is du over 5. So I'll just put it here, du over 5. Okay. Is this easier? I think this might be a little bit easier to process. 5 times 5 is what? 25. So if we keep going, we can factor out that 1 over 25 and bring it out front. I'm going to distribute that radical, right? So that's to the power of 1. So it's like 3/2. So there's u to the power of 3/2 minus u to the power of 1/2. And then I think like a du like this. And I think this is something that we can actually integrate. All right. I'm going to kind of work over here. Matter of fact, let me I think we got it. I think we figured out the trick. All of these have some little trick or alternate whatever. A lot of them. And you just discover them as you go, kind of thing. Okay, because I knew there was some trick, and I was like, I know I'm aware of what it is. It just got to jog my memory. Okay, so I think this is something that we can integrate, and this ended up being substitution. So the integral of what 3/2 becomes what 5/2. So if we calculate this, the 1 over 25 persists. That becomes what u. So I'll say times u to the power of 5/2 over 5/2 minus u to the 3/2 over 3/2, right? Like that. And then we'll say plus some constant. Okay. So 5 over 2, 2 over 5. Okay. So it looks like that becomes 2 over 125, u to the power of 5/2 minus 2 over 75 u to the 3 halves plus some constant. Okay? And then we back substitute our u. So then it looks like it's 2 over 125 times this, 5x plus 1 to the power of 5 halves. I'm going to shrink all this and get it on one line in just a moment. Minus 2 over 75, 5x plus 1 to the power, let me clean it up, plus 1 to the power of 3 halves plus some constant. Again, let me get this on one line. So I know that one was a little intense. I just had to remember the trick. And the trick there, we ended up doing substitution to get to the end. I'm going to shrink this one down just a little bit more because it's longer than everybody else. Let's go like here. Oh, I think you're still connecting. Okay. And then what we'll do, let's like expand it back. And again, we can check if we like take the derivative. I'm just trying to expand it as much as I can. I can move that guy. I think we're good. Okay. So we got something like this. And again, we ended up doing substitution instead of integration by parts. We tried integration by parts, but it wasn't working. So then something was like, well, something said, okay, well, just try substitution. So we let u be 5x plus 1. So then our du ended up being 5dx. And we can also write x in terms of u. So then we, after those changes, we accounted for them. And then we got it into a form that we could integrate. Did I do my integrations properly? And I feel like I didn't. Du is 5dx. We captured the 5dx. I feel like I'm missing something. 3 halves. I think, let's just check. I feel okay. And I mean, again, I could check by taking the derivative. I am being a little bit lazy. I'm going to use my prepared notes and see what happened there. Okay, so if we use our prepared notes, they said let u equal x and dv, this integration by part gives us this. Oh, they did integration by parts. Okay, let's see if that worked. Well, it must have if they got to the end. Oh, and our numbers are a little bit off. No, I think we just got it wrong. We got the 3 halves and the 5 halves. We're not that far off though. 2, I'm missing a 2 there. My x, I got some things wrong. So let's see what they did. So if our u is x, our dv, the integral of this guy, right? 1/2, so they add 1 divided by the new one. I didn't even bother to try to integrate this, right? I didn't even bother trying to do that. So it became 3 halves over 2 divided by 3 halves. Why does it feel, where'd that 5 come from? Oh, and then you gotta say divided by the derivative of that guy. Yeah, we didn't even bother trying to integrate this. We should have tried to integrate, and we could have kind of done like a guess and check. So we were close, but we're definitely missing some things there. Like this guy, I think these are off, and I think that's off. And I didn't check it by taking the derivative. If I had taken a derivative, I probably would have seen it right here. So 3 halves over 2. There's something we're missing with those integrals. Give me just a moment. Let me think about it. 3 halves over 2. So we reverse 2 over 3 times the 1 over 25. We're getting 2 over 75. So yeah, it's this part that's throwing us off, that we're missing something there. So the integral of u to the half is u to the 3 halves over 3 halves times Okay, right here. Right here. So like I'm trying to work through this u to the 3 halves, right? And when we integrate that guy, right? Or the u to the 1 half, we're getting u to the 3 halves over 3 halves, but there's a part that we're missing because of the x. Right? We're getting like 2 over 3 times u to the 3 halves. But right here, they're getting 2 over 3 right here. So what we can do, I think what's missing here, if we back substitute, we're going to have our 2/3 times, what was it, 5x plus 1. That was our, what was the u? Like we're getting this guy, right? But when we go to take the derivative, there's going to be an extra 5 in there, right? And that's all we had to do. Once we got a result like this, we should have checked by taking the derivative. When we go to take the derivative, this is going to be gone. That's going to become a half, and there's going to be an extra 5 in there, right? So in order to account for that extra 5, we would have to divide by 5, and that's where this 15 is coming from, right? Because I remember we had to do something like that before. We should have checked it by taking the derivative. We would have seen the extra 5. So then we're like, oh, we need to divide by 5 so that it'll work out properly. So that's where the extra 5. I'm going to leave those notes there so you can follow it, right? But just trying to discourage you from being intimidated to like try to integrate this guy. You get a result, just check it before you move forward. You'll see the extra 5, so then you need to be like, oh, I need to divide by 5 to account for that extra 5, so it'll work out properly. So then that covers this guy. This was the one that was kind of tripping us up. Then from there, we see it here. And then once you have that extra 5, I think all these others work out as well. Now let me see here. Oh, and then this one lost the x, right? So this one was we can take the integral here. Because then you're going to have, what, 5 halves over 2 right there. And this is going to be a similar procedure. The same way we got the 5 here is going to happen again here, and then you can kind of catch it. So what we have before, I think, is wrong again. We didn't check it. We are missing the 5. I found what I was missing. It is the 5. I'm going to strike through this. But, and it's really, and I'm going to highlight the part that we're missing in purple. Basically, this guy was the 5, right? That's what we're missing. But then everything else, I think, was fine. Now, let me see this. It's actually not far off. It's just a matter of accounting for that 5. Let me see if I have that there. Yeah. Anywho, while you live and you learn. Let's try another one. Let's see what else we got. Yeah. And again, I should have checked it. Again, just being lazy, I didn't check it. So. I think we did this one earlier, right? Except for it was a indefinite integral. I'll just do it again. It's fine. So let's see. Our u, it was like this. So then we need to find our du, our v, and our dv. Our dv was like dx. So that means this was x. This was dx over x. Okay. So then our u dv is there. So now we do our uv, which was x natural log of x minus the integral, so x goes from 1 to 2 of what, v du, which is just dx. Because when you say the v times the du, the x is canceled, right? So then that's going to be x natural log of x minus x. And we're going to evaluate this as x goes from 1 to 2. Okay. So it looks like we have 2 times the natural log of 2 minus 2 minus, I think the natural log of 1 is 0. So it's like it's minus a minus 1, which is like this. So then it looks like it's 2 natural log of 2 minus 1. All right, well, let's see how we did on this one. Now, this one I think we could actually do in our calculator. If anybody wants to see those details, I can do it. I'm just going to use my prepared notes. We got 2 natural log of 2 minus 1, which is correct. Okay, that one was. Let's give this one a go. Let me see. So life science population decay. It says the rate of change in the population of bacteria T hours after antibiotic treatment begins is estimated by this guy, where P prime is the rate of change of the population in thousands of bacteria per hour. Okay, thousands of bacteria per hour. Assume that when the treatment begins, the population consists of 1.5 million bacteria. Find the population of the bacteria after 24 hours of treatment, and then what is the total change of the population of bacteria from 24 to 36 hours after the treatment begins? Okay. Population of bacteria after 24 hours. So we have the rate of change, so they're basically asking us to take the integral. Okay, let me get some space. This is slide 21. We still got a good amount. Let's copy. Paste. Okay. So we have this what? P prime is T e to the negative 0.04 T. Just gonna pull that. Okay. So then for P of T, that's gonna be the integral. I'm just gonna do the generic one for now. T e of negative 0.04 T. Okay. So let's see if we can do integration by parts here. Okay, so at first glance, I'm tempted to say, let's let our U, I'm thinking is e to the negative 0.04 T, then our du, and then our v, and our dv. Our dv, if that's the case, we need a dt right here. So then our dv would be t dt. Okay. So if that's our dv, that means the integral of that guy would be what? T squared over 2. Is this helping us or is it making it worse? Do we need to switch these around? You know what? I think I'm going to move these around. Because I think that what we have now, nothing is reducing down. It's kind of making it worse. So I'm going to rearrange it. I'm going to choose a different order. Okay. I want my dv to be this e 0.04 t dt. I want that to be my dv. And so then that means my u would be t, right? So then my du would be what? dt. And the integral of this guy should be itself, I think what, divided by the derivative of the power or something like that? Because if I take the derivative, it's going to be itself times the derivative. So I need to divide by that negative 0.04, right? So if I take the derivative, it's going to be itself times the negative 0.04. They're going to cancel, and we get our desired form, right? And so it was something similar with the last one that we should have done that we skipped, right? Something similar along those lines. But anyway, I feel good about this, so we're going to move forward. Okay. So then our what is it? U dv is already done. So then if we're applying the formula, it's going to be what? uv. So it looks like we're going to have this like negative t over 0.04 times e, negative 0.04 t. Okay. So that's our u times our v minus our v du. The integral of our v du. Our du is dt, so we got lucky there. Okay, I think this is reasonable. Looks like we got a double negative at place, so these guys are going to cancel each other out. That 0.04, we can actually just move it to the left side of the interval, right? So this is really just the integral of e, which is itself divided by the derivative of the power. Okay, so then the changes here, looks like we're going to have this 0.04 under t, e 0.04 t. We get that 0.04, we can kind of move to the front. So 1 over 0.04. The integral of e is itself divided by that power. Plus a constant. And for that last term, if I do a quick check, if I take the derivative, it's going to be itself times the negative 0.04. One of those are going to cancel, one is going to persist. And I think our sign works out properly. Okay. I'm confident in this one. You know, I'm just going to kind of keep moving forward. So then they wanted the population after 24 hours. So then if this is our P of T, then we would do P of 24. So just basically plug in 24. I am definitely going to use my calculator here.
I'm on my suit.
Right here. Okay. Now, what we could have done. All right. I'm tempted to just use the original, right? I'm going to say the original, that derivative is like x times e to the power of a negative 0.04x. Okay. And then I think the calculator can evaluate this. Maybe not. Like if we had the indefinite integral for part B, we can. Okay. I'm going to try something. Let me just see. I'm going to see if I can get it to work. So if I go to math, the integral, number 9, of that function we just typed in with respect to x, as x goes from now, we don't have the bounds. Let me think about this, if this will work. I'm going to say as x goes from 0 to x. I don't know that this is going to work. So we usually need the limits of integration. What if we did from 0 to 24 instead? Let's see how that works out, if that'll work. This may or may not work. I'm not confident in this. We got a result. So what I'm going to do, zero to 24. I think that's actually okay. The integral as x goes from 0 to 24. I think that actually might be fine. Yeah, I think that's actually okay. Okay, so I'm going to compare. Well, here, yeah, I'm just going to compare to my prepared notes. I didn't crunch those numbers. Did we get a negative there at least? We do have that. I'm just going to kind of go with it. We got this 155 after 24 hours. This is in 1,000, 155,000? Or I think it's 1,000. 0. Yeah, I think they're doing the 0 to 24. Oh, the starting amount. Okay, no, I think we're a little off. So it started with, yeah, they did give us a starting amount was like 1.5 million. So that's when the time was 0. So then that way we can solve for C. So we can go back and do that. Like that's not too bad. I was trying to figure out what I was missing. Okay, so the number that we have is no good. So the thing that we're missing, they gave us that it started with 1.5 million bacteria. So that means when the time is 0, we can use that to solve for C. And then we get a C of the 2125. And so then once we have C, now we plug in our function there. And we're good to go. So, okay, well, that's fine. That's not too bad. Okay, so what kind of, I guess we can just use that 2125. Let me go ahead and add that part. So again, the part that we're missing, I'll do it in, I guess, this color. My day. Right here, right? If we plug in 0, that first term look is gone because you have a 0 there. The second term, there's a 1. Let me see. That's 1. You have this basically we have this -1 over 0.04 squared plus C equals 1,500,000. All right. Let me calculate. Let me crunch that real quick. It should be like 2125. Now, if we did it in thousands, let's see, 1,500 instead of 1,500,000, we're going to say plus 1 over 0.04 squared. I think that should be okay. And we get our number. All right. So I'm kind of out of space. I'll just kind of write it here. 2125. So then with that C, now we have our function, right? On this line, I put at the blue star, right? That's our P of T. And we should crunch those numbers to make it look a little bit neater and cleaner. We kind of need to rewrite it. But again, I'm just kind of being lazy. Okay, I think we're good there. So then for part B, what's the total change in the population of bacteria from 24 to 36 hours after the treatment began? That one I think we can actually use the calculator, right? So if I go back, the integral of the original of that function with in respect to x is x goes from, was it 24 to 36? 24 to 36 hours. So right here we would say 24 to 36. I think that one we can actually do in the calculator. Total change 107,000. Let's see if we compare. There it is. Yeah, we got it. So, the TI-83 plus can evaluate integrals when it's a definite integral, you have those bounds. The reason we couldn't do it in part A is because we didn't have the bounds. So that's why that one was off. But part B is good. Okay, so I'm just going to use my prepared notes. Well, we did it in the calculator. Okay. We still got it. Well, let's keep going. We're almost there. Okay, let's see what else we got. Evaluate this integral to find the area of the shaded region below. Okay. As x goes from 0 to 7. Okay, so let's just try integration by parts real quick. U, du. Oh, okay, so I think this one, we got to do integration by parts twice, which can be a pain. All right, so I'm thinking let my u be x squared. So then we need to find our du. We're going to find our v. And so that means our dv will be e to the negative x dx. Okay. So if e is its own integral, let's see. If we let the integral of that guy be e to the negative x, when we go to take the derivative to check, we're going to have an extra negative in there. So we need a negative here so that it works out, right? So now when we take the derivative of this guy, the derivative of e is itself times the derivative of the power. So then the negatives cancel. We finish with the proper derivative. Okay, so we can have some confidence in this v. And then if our u is x squared, that means our du is 2x dx. Okay. So our u, dv, everything is there. Okay. So then when we go to apply the integration by parts, our uv, so we would have negative x squared e to the negative x. Okay. So that's a uv minus the integral of v du. V du. So it looks like it's a double negative. There's a 2, so I'm just going to move the 2 in front. X e to the negative x dx, right? Okay. So the reason we know we're going in the proper direction, again, I just remember this one was like a double integration by parts. It's similar to where we started, but notice that power has reduced by 1. So that means if we do it again, then we can get rid of that first factor, right? So let's just do it again. Let's keep going. So we're going to do integration by parts again. I guess I'll do this color. So now I'm going to let my u be x. So we need to find our du. And then we're going to find our v. And that means our dv would be e to the negative x dx. Okay. So the integral of that is going to be e to the negative x. I think we needed an extra negative in there. So when we take the derivative, we get itself back times the negative, double negatives cancel, we're good to go. The derivative of x is just dx. Okay. So then when we apply integration by parts again, the first part just persists. Now we got this 2 uv. So I'm going to go like this. Negative x e to the negative x minus the integral of v du. So double negative is a positive. E to the negative x dx. Okay, so now we're pretty much there. E to the negative x we can integrate. I'm going to kind of work over here. I know our spacing's kind of weird. So it looks like we have this negative x squared e to the negative x plus, I'll say 2. We still have this negative x e to the negative x. Integral of e to the x is itself e to the negative x. But I think we need an extra negative in there. And we need to evaluate this as x goes from 0 to 7. Man. All right, the whole thing is x goes from 0 to 7. Kind of like this. The 0, the 0 is going to have something in there as well. We probably should give ourselves some space because we need to plug in when x is 7, we get something. When x is 0, we get something. What's the time? I got like a solid 10 minutes. I'm going to try it here. When we plug in 7, this is going to be a negative 49 e to the negative 7 plus 2 times, what is that, a negative 7 e to the negative 7 minus e to the negative 7. So we get some answer there, right? All of that. I know we're out of space. I'm going to say minus, when x is 0, that first term is gone. That's gone. Looks like we get 2 times negative 1. So it looks like we get minus. This is like minus a negative 2, so then plus 2. Man. So then we need to go and crunch that line. Find the area. Okay. So that's the exact answer we get, and then we would use a calculator. Let me reduce. I should generate some space. That would be better. Let's see. So at that point, it's really just a calculator. Let's see if we can, let's just try it. Let's just try it. Now, we could just put the original in there, and since we have those bounds, we could just generate a number. I'm gonna check the work that we did, and I'm gonna do what's the more simple technique, and then they should be the same number if we did it proper. All right, so we got this negative 49 times e to the power of negative 7, okay, plus 2 parentheses negative 7 times e to the negative 7, okay, minus e to the negative 7. Close off the parentheses. Let me see. Open, open, close, open. Open, close, close. 49. Okay. I'm going to put one here, and I'm going to say plus 2. We get an answer. Okay, we get that answer. So then what I'm going to do to check this guy, I'm just going to compare it to the original. So what I'll do, I'll say my x squared times e to the power of negative x, okay? And I'm going to go math. It's number 9. I want to take the integral of that function that we just typed in with regards to x, as x goes from 0 to 7. And hopefully we get the same number. God is good. So we can be confident. That's about the best we can do, right? So we got an exact result, we got an approximation, and we compared the two to each other, and we got the same thing. So we got approximately 9407. Oh my goodness, come on. Okay, so I want to compare to my prepared notes. Let me see. So let u be x squared, right? Yep, I think we did all that. We get a result. To evaluate the integral on the right, we can apply integration by parts again. Now they said, yeah, the 2x, we kind of did a little bit different, but we still got the same thing. Okay. This is a lot cleaner. There it is. This is the line. This is the line that we got to is here, something like this. And then they just factored out the negative e to the negative x, right? But we essentially got this. 1.94, I think that's what we got. Okay. So that one is an adventure, right? So you saw us do it together. The main takeaway there was we did integration by parts twice. So you did it, and the way you can kind of recognize it was that, you know, this factor here, the power was reducing, right? When after we did integration by parts once, then again, then that term should be gone, and we can finish out the interval, right? That was the takeaway here, was this guy. Okay, so you know, these are intense. I mean, again, this is why I do unlimited attempts, a minimal late penalty. You know, try to encourage you all to work together. You know, it's okay. Like, it's okay if you work together, because I'm not really trying to, like, the intent is, I'm not trying to like be super rigorous here. I'm really just trying to expose you to these concepts and try to encourage you all to learn as much as you can. And you know, if you collaborate, it's okay. Like, it'll be okay. Like, it will be okay. Right. I'm really just trying to expose you to the concepts and then, you know, allow you an opportunity to practice. We got about 5 minutes. I think I'm done. Oh, well, let me see. Now, when you try the integration of parts on this problem, you'll notice a pattern. Using tabular integration can greatly simplify your work. So you can do integration by parts, but you can do it in a table where you can see a pattern. I don't know the nuances of the table, so I'm just going to use my prepared notes right here. I just want you to see this though. So you have f and repeated derivatives, the sign of the product, and then g and repeated integrals. Okay. Okay. So then add the products along the arrows, making alternate sign changes to obtain this. Okay. So again, we had our F versus our G, where our G was what we're gonna keep taking the integral of, and in that case, our G was e to the x, and we let f of x be that power function. So then when we do the repeated derivatives, they eventually go down to 0, but the integrals stay the same. So then the sign of the product, they alternate. And then it says what, multiply along the diagonal, or add the products along the arrows, making alternate sign changes. X cubed times e to the x. So it should be a negative 3x squared e to the x. Okay. And basically alternating sign changes. 6 e to the x. Okay. So the table is just a shorthand version of like the multiple integration by parts. That's all it is. Okay, I think that's enough for one day. We know we had some thrills and chills and spills. You know, you can't get everything right. And that's the beautiful thing about being a human. You're allowed to make mistakes. Like, it's okay. Like, just do your best, right? Because if you're not allowed to make mistakes, then you're not a human. You're a bot, right? You're a robot. And we're not human doings. We're human beings. We're allowed to be. Trial and error, that's our nature, right? We can push the limits, but eventually we come across that. Okay. So yeah. So we are here. So again, that was a culmination of the new material that you're responsible for. I might do a bonus lecture on Wednesday. It just depends on if I pull the information and get it up there. But you're only responsible up to 4.6. Definitely next week, we'll start reviewing. I want to say that exam 2, again, should become available this Sunday. So we'll take next week as an exam week. I mean, we're pretty much doing a review from here from here all the way until the end. Let me see. Let me pull up a calendar real quick. Let me just pull up a calendar. So today is the 7th, right? If next week is exam 2, 1, 2, 3, 4. It's kind of like some repeat review sessions in there a little bit. If we took all of next week to review for exam 2, you'll have access to it, and I'll probably just take class time. I'll just take class time during next week to review for exam 2, to provide an opportunity for you all to ask questions. And then after next week, we got 4 sessions. So I think it's the 21st, the 23rd, the 28th, and the 30th. And basically, each of those days I'll review a chapter, right? So the 21st, I'll probably review chapter 1. 23rd is chapter 2. 28th is chapter 3. The 30th is, and that's our last day of class is the 30th. We'll review chapter 4. The reading period, I think, is May 1st and the 2nd. And then the final exam should become available that Sunday, May 4th, and is due that Friday, May 9th at 11:59 p.m., right? So the last time we meet is that Wednesday, April 30th. And then we have the reading period for those 2 days. The final, again, you should have access to the final for about 5 days, 5 or 6 days. And then the hard deadline for everything is that Friday, May 9th, right? So beyond that date, beyond that time period, that Friday, May 9th at 11:59 p.m., then on our end, we have to start crunching final grades, right? So this is a good time to get caught up and things of that nature. Are there any burning questions before we go our separate ways? I feel like there should be questions. Today was, it had its challenges, but, hopefully we learned something and we can grow. If there aren't any burning questions, we're going to go ahead and end the session here. Now, from one beautiful mind to another, enjoy your evening, and hopefully I'll see you all tomorrow at our awards day ceremony. So, I'm not expecting a big turnout because a lot of my students are remote. So if they don't check their email, then, they're not going to know about it. But I do have at least one RSVP. Go ahead.
Can you resend that email because I didn't get it?
Oh, okay. Let me try to send it again. Okay. Mr. Winston, right?
Yes, sir.
Okay. Let me send it now.
I would like it as well. I didn't receive it either.
So if I go back to my sent, Thursday, maybe it was Tuesday. Did I miss? Okay. I know I sent it. Let me see. I gotta find it. So I'll type awards day. Okay, guys. So just give me a few minutes. If you don't get it like by maybe 10 o'clock tonight, then just call my office cell phone number because I got I do need to get ready for another class, and I'm not seeing it immediately.
Okay.
Uh-huh. Okay. All right, guys. Take care. Were there any other questions before we went our separate ways?
No, sir. Take care.
All right, I got to figure out where is this thing. Let me see what's going on here. Chat.